In this lesson, we're going to be taking a look at linear functions. So we'll start out with a definition and tell exactly what they are. A linear function, quite simply, is a non-vertical function with a constant rate of change. Typically, we write this in the form of y equals mx plus b. Now, we see in here the existence of four variables: y, m, x, and b. Y and x play their normal role. Y is the output, x is the input. M and b have the special characteristics of b being our starting point, or also known as our y-intercept, and m is our rate of change. Shown below, we have two different functions. Our first, you can see, is a linear function. It forms a straight line and it has a constant rate of change. The equation written here, f1 of x equals a negative 1/2 times x plus 3. Negative 1/2 is our rate of change. 3 is our starting value, and if we look, this function intersects the y-axis at the point 0, 3. The 1/2 tells us our descent rate. It's going down half a step for every one step it moves over, or it's moving down one step for every two that it moves to the right. Our second function is a nonlinear function. We can see that we have a constant changing of the function. Sometimes it is moving up, sometimes it is moving down, sometimes it is perfectly flat. This is y, or f of x is the sine of x minus 2. So this is something that we will get to later in our study of mathematics, but does not qualify as being linear. So we're not going to regard ones of that nature, but we do need to be able to identify them in terms of graphs, equations, and tables. And here are some of those functions. Now, some of these are linear and some are not, and we're going to go through and identify the pieces and parts that are. So, as we look at our values, let's see if we can find a constant rate of change. Now, in order to calculate rate of change, we're going to call this our slope. We have to have a constant change of y divided by change of x. The triangles that you see here are the capital Greek letter delta and is used in mathematics to signify change. So, how do we move from 16 to 4? And that's minus 12. How do we move from 4 to 2? That's minus 2. How do we move from 2 to 1/2? That's minus 1.5. Now, what's happening on the other side? To move from 1 to 3, that's plus 2. To move from 3 to 4, that's plus 1. And from 4 to 6, again, is plus 2. So it's not so much that we have differences in our changes, it's what is the ratio of these changes. So our first one, we have negative 12 divided by 2, which is a negative 6. Our next one, we have negative 2 divided by 1, and that is negative 2. Next, we have negative 1/2 divided by 2, and that gives us a negative 0.75, or negative 3/4. Because our rates of change are not always the same, this is a non-linear function. So no, this is not what we're looking at right now. Let's see how this works on our next one. From 3 to 5, that's plus 2. 5 to 7 is plus 2. 7 to 9 is plus 2. So those are being consistent. Let's check our other side. From 0 to 1 is plus 1, 1 to 2 is plus 1, 2 to 3 is plus 1. So if we take the ratio of these sides, 2 over 1, our change of y, 2, divided by our change of x, 1, we have a slope of 2. Next, 2 over 1, it is 2. 2 over 1 is also 2. So this one is linear because it has that constant rate of change. Now what does this look like in terms of writing out equations? Remember, when we write the equation, it will be something along the lines of y equals mx plus b. Anything that can be written in exactly this format is linear. So take a look at our first one. Y equals 3x over 5. Does this qualify? Well, anytime we are multiplying or have a fraction, we can write it such that is just the fraction times our variable, which would be like a whole number. So x divided by 1, when multiplied by 3/5, would be 3x over 5. Does this qualify as being of our linear type? Do we have this format? Well, I see my y, I see my m, it's 3/5, I see my x, I do not see a b, but anytime we are adding, we could always add 0. So yes, this is linear. We have a constant rate of change, and we do have a y-intercept given. Next, y equals x plus 9. I see the y, I see the x, and I see the b. Do I have an m value? Well, anytime I have a single variable by itself, I could write it as y equals 1 times x plus b. So my slope in this case is the number 1, and I would say yes, this is linear. Last one of our set here, y equals 17 plus 2 to the 3x power. Well, I'm going to rewrite it so that my x comes first, and I come out with y equals 2 to the 3x plus 17. And right away I notice some differences. In my linear function, I have it written as the form of y equals mx plus b, where x is a multiplier of my rate of change, or my slope. In this function, my x is part of an exponent, and I don't have that anywhere else. So I'm going to say no, this is non-linear. This is what's called an exponential function. We will get to these later in our study of mathematics, but at this point it is not what we're working on, is not a linear function. Now let's come up with some vocabulary terms to work with. Solution to a linear function. A solution to a linear function can be defined as an ordered pair of numbers x, y that makes the equation of the function true. So if I'm looking at a function such as y equals 2x plus 7, a solution I could propose to this would be the number set or the ordered pair 1, 9. And then I need to check to see if this is true. What I would do is I would substitute in the first number for my x and the second number for my y and see, is it true. So 2 times 1 is 2 plus 7 is 9. So if I substitute in the 1, I do indeed get 9. Yes, this is a solution to this function. Next, discrete domain. And this is a domain set, or my input x values, of a limited definite value, graphed as a set of separate points. So anytime I have things that exist in isolation with no connecting values in between, I have a discrete domain. A lot of times this will be used in terms of sales of items, when counting people, because even though in the United States we say there's an average of 2.3 people per household, you can't really have 3/10 of a person. So when we count actual people, we have to count whole individuals, and that is a discrete domain. Last here, a continuous domain, which is a domain of infinite values with possible upper and lower bounds, graphed as a connected line. And what I mean by it being both infinite and having bounds is that I can be working in a function, so a quick graph, and then have it be everything from a certain starting value to a certain ending value, but everything in between. Every small change, every rational number, every irrational number between that start and end point are possible solutions, such as traveling home. You cover every distance in between, the passage of time. You were 10 years old at one point, now you've achieved the age you are. You didn't just magically appear there, but you did cover every space in between. These are going to be continuous domain items. When we do graph it as a connected line, and we'll have all those small values. So let's take a look at a couple of situations and see if we can write equations and decide on the types of domain we're looking at. First, a hot dog vendor sells his product for $3.50 each. Write a function of the cost y for x hot dogs. Is this domain discrete or continuous? So let's begin with our function. Our basic premise is y equals mx plus b. Now the variables can change, but in this one we are told specifically we are to use y for our output and x for our input. Next, we need to figure out our slope. What is the rate of change with each new, in this case, product or hot dog that is purchased? And we are told that that rate of change is $3.50. If I buy one hot dog, it's $3.50. If I buy two, it'll cost me another $3.50. So, translating this down, y equals 350 x plus b, and what is our start? Well, if I don't purchase any item, then it's not going to cost me any additional amount. So, b is taking on the value of 0. So our end equation is y equals 3.5x, or 3.5x. We could write the full 350 if you would like to keep in mind that this is a money item, but that is our equation. Next, is this a discrete domain or a continuous one? And the question we have to ask is, do fractions or decimals of this situation make sense? X is the number of hot dogs purchased. Can I purchase a tenth of a hot dog? Can I purchase a quarter of a hot dog? And the answer is no. The person selling is going to sell me a whole hot dog or no hot dog at all. So because those partial values do not make sense, this is a discrete domain situation. Let's take a look at our next one. A student lives 3 miles from school and walks home at a rate of 4 miles per hour. Write a function for the remaining distance, d, for h hours of travel. Is this domain discrete or continuous? So let's look at our situation. Well, our values, or our variables, starting with our basic of y equals mx plus b, have been given d and h instead of x and y. So the remaining distance, d, is going to be defined as some sort of change of h. Rather than x and y, we're using h and d. And what are our situations? Well, we can walk home at 4 miles per hour. If home is our reference point and we are walking towards it, then we are going to be taking on some sort of movement coming in. So we're going to have a negative 4. Negative showing that the distance is decreasing as time passes. Now we need to figure out what is our y-intercept, or our starting point, and since the student lives 3 miles from school, we're going to start out at a distance of 3 miles. So d equals negative 4h plus 3. Now, is this discrete or continuous? Since we're looking at the passage of time and the distances that we are away from home, we don't magically disappear from one location and reappear at another as a teleporter would. We actually do have to travel the distances in between. So this is a continuous function, or a continuous domain function. It's not just isolated points. We're not 3.5 miles from home, then all of a sudden we're 2 miles from home. We do physically have to travel the spaces in between. So we end up with that continuous, connected path of travel and function. So look over the vocabulary here. Look at the different ways that we can find if a function is linear based on graphs, equations, situations, and tables of values, and be ready to identify and use these different points and concepts.